What if I told you that every time you get paid, transfer money, or even file your taxes, you're depending on a computer language first introduced in 1959? A language most people assume died out decades ago is still quietly processing billions of transactions every single day. The strange part is, very few people alive actually know how to maintain it. When New Jersey's unemployment system buckled in 2020, headlines blamed COBOL. But in reality, failures often came earlier, with overloaded web portals and servers hitting fragile backends. Still, the crisis proved one thing: ancient code can bring modern systems to their knees. When cracks appeared in New Jersey, the breaking point became visible in April 2020. Businesses had shut down almost overnight, and millions of workers were suddenly applying for unemployment benefits. The scale was staggering. In the first week of April alone, 6.6 million new unemployment claims were filed nationwide, shattering every previous record. For states like New Jersey, that spike translated into backlogs of millions of applications, far beyond what their systems had ever been designed to handle. At first glance, it looked like a typical overload problem. Too many people trying to log on at once. Websites froze, phones rang endlessly, and servers strained under the traffic. But servers can be expanded. What couldn't be expanded so easily was the fragile foundation of the unemployment system itself. Buried beneath layers of modern web interfaces was an engine written decades earlier in COBOL. Every benefits calculation, every claim update, every stored record relied on routines that hadn't been touched in years. Under normal conditions, they ticked along unnoticed. But when the surge arrived, the smallest lag cascaded outward until the whole system seemed paralyzed. For thousands of families, this wasn't just a technical snag. It meant rent checks delayed, groceries harder to buy, and health costs stacking up. Citizens refreshed web pages, dialed hotlines, and waited through recorded messages that never connected them to a solution. The state had the money to pay, but access to it was literally locked inside a computer program. What most people didn't realize at the time was that fixing this wasn't as simple as rebooting a server farm. It required people who still understood the logic of the old code. The shortage of those people quickly became national news. In a press conference, New Jersey Governor Phil Murphy openly asked for volunteers who could program in COBOL, a language more than half a century old. The request caught attention not just because of the unusual skill set, but because it revealed how unprepared the system really was. Imagine being asked to repair a Model T engine to keep highway traffic moving. A few decades ago, mechanics who could do it were everywhere. By 2020, many had retired, and those still active often hadn't touched COBOL in years. Still, it's worth clarifying that the meltdown wasn't entirely COBOL's fault. Analysts later pointed out that some visible errors came from the more modern layers, like Java-based front ends and overburdened web servers. Unemployment systems aren't just one computer. They're a stack of technologies where front-end glitches can ripple back to mainframes. But the COBOL core mattered enormously, because when new federal rules from the CARES Act expanded eligibility and payment amounts, those changes had to be written directly into the old programs. Without skilled programmers, the bottleneck was unavoidable. This mismatch between public expectations and system reality was jarring. Citizens were used to smartphones powerful enough to stream video calls and run complex apps instantly. Yet the amount of unemployment money a person received still depended on lines of COBOL, written when computers filled entire rooms and were fed instructions on punch cards. The pandemic simply exposed the gap between modern convenience and unseen infrastructure that had aged in place. For many, this was the first time they had ever even heard of COBOL. Suddenly, reporters, politicians, and tech circles were voicing its name daily. The language wasn't failing in the sense of breaking down. The math still worked, the system still stood. The problem was human. Too few people knew the code anymore, and that scarcity translated into very real consequences for families waiting on vital payments. It was a collapse driven by skills, not by silicon. What New Jersey's crisis revealed carried a sharp lesson. Code is not just an academic exercise or something happening behind screens. It is infrastructure, as critical as roads or power lines, and it weakens when ignored. The unemployment system wasn't the result of hackers, outages, or lost money. It was an issue of legacy design combined with decades of neglect in maintaining expertise. The shock was not only that such old code still ran in 2020, but that so much depended on it functioning correctly under pressure. If a language written in the late 1950s still held the power to determine who received unemployment checks, then it raises deeper questions. Why did it last? What made people trust it deeply enough to run essential services on it for generations? To understand why that old code endured so long, and why operators stayed committed to it, we need to meet the person who helped make programming readable in the first place. The moment Grace Hopper changed programming forever. Computing in the 1950s was locked away behind walls of symbols and mathematics. To operate a machine, programmers had to feed stacks of punch cards into massive computers, each card crowded with codes and zeros, ones, and cryptic abbreviations. These machines filled entire rooms, but only a small circle of trained specialists could speak their language. For everyone else, bank clerks, managers, administrators, they were mysterious systems that needed an interpreter just to function. Grace Hopper saw that wall and decided it didn't have to exist. A U.S. Navy officer and one of the earliest computer pioneers, she asked a question no one else was asking. Why couldn't computers understand words closer to normal English? While working at Eckert Mauchly in the early 1950s, she developed one of the first compilers, a tool that acted much like a translator. Instead of expecting humans to memorize machine instructions, the compiler would convert plain language commands into binary code the computer could follow. The idea sounded almost unreasonable at the time. Many colleagues dismissed it as too ambitious or inefficient. But Hopper pressed forward. She proved that compilers worked, showing that writing add or move in a program could become the same precise instructions the machine needed. It was a breakthrough because it changed the frame of the problem. People didn't have to adapt to computers anymore. Computers could adapt to people. By the late 1950s, those efforts converged into something larger. In 1959, Hopper played a central role in defining COBOL, the Common Business-Oriented Language. It was designed not for mathematicians, but for businesses and governments that needed computing power without years of technical training. COBOL's code used simple, readable commands and sentence-like structures that mirrored business logic. A payroll clerk who understood the steps of cutting a paycheck could now look directly at a COBOL program and follow its reasoning. That accessibility mattered. Before COBOL, computers were an intimidating investment, often viewed as impractical for offices where most staff weren't technically trained. With COBOL, the barrier collapsed. Banks, insurance companies, and government agencies suddenly had a language that worked across departments. An accountant didn't need to grasp machine code to recognize what the program was doing, because the commands themselves resembled the way they already thought about numbers, payments, and records. The promise of a shared language was what Hopper had envisioned years earlier, and supporting industries quickly saw its value. Instead of relying on small teams of mathematicians to maintain arcane systems, COBOL allowed everyday professionals to engage with computing outputs directly. If you were managing payroll or processing insurance claims, you could at least read the code, follow its processes, and trust it to reflect real-world tasks. This shift had wide consequences. Because COBOL was meant to be understandable, it spread rapidly through business and government. It wasn't the most elegant language from the perspective of computer scientists, and specialists built other systems for scientific or technical work. But in the economic centers where money, records, and compliance mattered, COBOL became the standard. Its English-like design didn't just lower the barrier, it created confidence. And confidence was what institutions needed to place computing at the heart of their operations. The result was a quiet revolution. Computers moved out of lab environments and became embedded in everyday administration. Hopper's vision, making code human-readable, transformed how industries approached new technology. What once looked like a mathematical black box turned into something organizations could recognize and trust. And once trust was in place, adoption followed. By the early 1960s, COBOL was no longer experimental. It had been selected as a government-backed standard, and businesses across the country began using it to handle payroll, taxes, and record-keeping. For the first time, non-specialists could see a program and understand the flow of instructions without translation. That readability gave them confidence, and once confidence took hold, COBOL set down roots that would prove nearly impossible to dislodge. This is why COBOL endured. It wasn't because it was flashy or technically superior. It was because it gave people outside the technical elite a point of entry. It let computing slip into the workflows of banks, offices, and agencies in a way that felt natural. Hopper had wanted to open the door to computing for everyone, and COBOL was the language that made it possible. And once that door was open, the transformation accelerated. Institutions began running daily life on this new foundation: paychecks, taxes, insurance, even airline reservations, all written in a language designed to be readable. The strange part, though, was that while everyone depended on it, hardly anyone saw it. The code itself disappeared into the background, quietly shaping how economies functioned without drawing attention to itself. COBOL, the invisible backbone of our economy. By the early 1960s, COBOL had already begun moving beyond experimental projects and into everyday use. Banks, insurance companies, and government departments were investing in mainframe computers. And COBOL was the language that made those machines useful to entire organizations. This is where COBOL truly became the invisible backbone of the economy. Mainframes were enormous, costly machines, stacked with tape reels and humming with power. Institutions bought them to speed up work that human clerks with ledgers could no longer manage. Huge payrolls, millions of tax records, and streams of transactions piling up every day. The hurdle was always communication. Traditional machine code was full of symbols and numbers that only trained specialists could follow. Hiring armies of mathematicians to build custom systems for every payroll and tax office was not realistic. COBOL solved that barrier in a way no other language could. It replaced cryptic commands with words that mirrored office logic. Instead of arcane lines of code, a payroll program could literally say add hours or subtract tax. This clarity let business staff follow what the system was doing, without needing a translator. Managers could look at a line of COBOL and immediately connect it to the policies they already enforced. That practicality is what made adoption snowball so quickly. The results showed up across industries. A retailer could suddenly run payroll for tens of thousands of employees each month without exhausting teams of bookkeepers. Tax agencies could standardize how returns were calculated, reducing inconsistencies between regions. Airlines migrated from paper ledgers to automated booking systems. Almost overnight, COBOL became the tool that kept paychecks, records, and tickets flowing on time. It was never flashy technology, but it didn't need to be. Its greatest strength was that it quietly turned human rules into predictable outcomes. Very few people noticed COBOL directly. They just knew their paycheck was deposited when it should be, or their bank balance updated after a deposit. Even as airlines moved millions of passengers per year, COBOL stayed behind the scenes. There was no logo or company fronting the brand. It simply worked with such consistency that people stopped thinking about what was underneath. That's where trust began to build, not through advertising, but through daily reliability. This dependability shaped organizations' decisions over decades. Once a payroll or tax system stabilized under COBOL, there was little reason to replace it. Companies might swap out the hardware or expand memory, but the code itself remained intact. Rewriting everything raised the risk of errors in systems where mistakes were unacceptable. Year by year, patches were layered on top, yet the heart of the original COBOL stayed the same. Industry estimates now suggest over 220 billion lines of COBOL code are still in use worldwide. A staggering figure that reflects just how much of modern life still relies on it. That ongoing reliance wasn't limited to payroll or taxes. COBOL carved out a lasting place in global finance. Industry estimates suggest around 80% of in-person bank transactions still rely on COBOL systems. From daily withdrawals at ATMs to transfers between institutions, decades-old COBOL programs process the money flow behind the scenes. With that level of entrenchment, businesses and governments saw COBOL less as software and more as infrastructure, something you trusted like power lines or bridges. And once code becomes infrastructure, replacing it feels nearly impossible. This success had unintended consequences. The very traits that made COBOL attractive, clarity, stability, and invisibility, made institutions reluctant to move away from it. What started as an advantage became a form of digital concrete, systems so durable and embedded that businesses feared making changes at all. The longer COBOL ran without failure, the harder it became to justify modernization, even when technology elsewhere was advancing rapidly. And it's here that another story begins to emerge. The reliability that made COBOL indispensable also laid the groundwork for a problem no one anticipated. Those same qualities created systems too critical to touch, and that dependence would shape how industries faced crises in the decades to come. When reliability became a trap. How can strength slowly turn into a trap? That's what happened with COBOL, a language adopted because it was stable and readable, but eventually so entrenched that it became almost impossible to replace. For decades, it powered payroll systems, processed bank transactions, and issued government benefits without interruption. Yet the very reliability that made institutions trust it also locked them into a cycle of patching instead of rebuilding. Over the years, experts began to describe this as digital concrete, legacy systems where decades of patches and exceptions had been layered on top of old code, making complete rewrites both risky and prohibitively expensive. Imagine a pension system built in the 1970s. In its early version, it calculated contributions and mailed out checks. Soon, tax laws added new formulas, so programmers bolted those in. Inflation adjustments needed handling, then survivor benefits, then disability credits. Each new rule was slipped in as an add-on instead of rewriting the core. By the 1990s, the program stretched across hundreds of thousands of lines of COBOL. If you changed one section at the bottom, there was no guarantee another rule above wouldn't break. Every modification carried risk, so managers often felt safer, leaving the fragile whole untouched. This pattern repeated everywhere. Insurance companies inserted riders and new policy categories. Banks added routines for credit cards, global currencies, and changing regulations. Governments appended deductions, exemptions, and reporting conditions. None of these changes were small. They represented years of cumulative adjustments piled on older frameworks that had never been dismantled. The result was immense complexity hidden beneath a surface that appeared to work fine. The paradox was simple. COBOL systems functioned reliably enough that rewriting them from scratch seemed unnecessary, but they were also so old and patched that touching them became dangerous. Costs made that dynamic worse. Proposals to modernize often involved budgets in the billions and years of retraining entire departments. Faced with that, executives usually chose the safer and cheaper option in the moment. Keep patching the systems they already trusted. That instinct turned COBOL into bedrock. Solid, dependable, but immovable. By the late 1990s, nearly every major financial institution and government body had essential operations encased in this digital foundation. Then the calendar exposed a hidden weakness. As the year 2000 approached, a quirk buried in millions of COBOL programs suddenly carried global consequences. To save memory in the early decades, most systems stored years in 2 digits, 99 for 1999. But what would happen once the clock rolled to 00? A program might interpret it as 1900, not 2000. That meant a mortgage could appear a century overdue, or pension payments might be denied because a retiree seemed not yet born. Across finance, government, and transportation, the risk of cascading failures was real. The Y2K problem made institutions confront how much they still relied on COBOL. Theoretically, the fix sounded easy, change date fields from 2 digits to 4. But execution was another matter. Vast programs written over decades had hidden thousands of date fields buried deep in their logic. Much of it was undocumented or written by programmers long gone. Every line had to be found, checked, and rewritten by hand. The job was mechanical but immense, literally scanning through millions of lines of code to catch every vulnerable reference before midnight struck on January 1st, 2000. The sudden scale of effort turned COBOL specialists into a scarce, critical resource. Retired programmers who hadn't written code in years were called back to service because they still understood the logic hidden in those decades-old systems. They combed through forgotten sections, repaired routines, and verified that changes wouldn't ripple into unexpected failures. I2K became an emergency project for governments and corporations alike, one that consumed billions of dollars in testing, remediation, and contingency planning. In the end, the fear disaster didn't happen. Planes flew, ATMs worked, and pensions were paid. It wasn't because warnings had been exaggerated, but because thousands of programmers worldwide identified and fixed the flaws in time. Y2K showed that legacy code could be shored up under pressure, but it also revealed how fragile dependence on COBOL had become. Millions of hours and extraordinary sums of money had been spent just to keep systems running into the new century. When January 2000 passed smoothly, many organizations relaxed. They had avoided immediate collapse, but their core systems hadn't changed. They were still built on COBOL, still burdened by complexity, and still dependent on a shrinking pool of specialists. Y2K wasn't a permanent fix. It was proof of how much work was required just to maintain the status quo. And that lingering reality points toward the next problem. What happens when the people who wrote and maintained this financial infrastructure retire, and no one remains who can read it? It's a challenge that only grows sharper as time moves forward. The knowledge crisis nobody sees coming. What happens when the people who know how to keep the world's financial code alive are gone? That's the knowledge crisis quietly building beneath the surface. The programmers who built COBOL systems in the 1960s, 70s, and 80s are now retiring, taking with them not just technical skills but also an understanding of why systems were designed the way they were. They know where obscure exceptions were added, how critical patches fit together, and where hidden risks might still sit. Without that insight, the code may continue to run, but the ability to adapt it grows weaker with every departure. Younger developers stepping into the field today are learning entirely different skills. Universities and online boot camps focus on Java, Python, and cloud frameworks tied to AI and mobile apps. That's where new career opportunities are found, not in languages written before the space race. As a result, COBOL feels less like a viable career path and more like studying a dead tongue. The gap is clear. While incoming developers look to the future, the systems that still process paychecks, taxes, and benefits remain anchored in the past. But those old systems don't disappear. Banks continue to manage deposits and loans through COBOL. Insurance companies track claims in it. Governments use it to run programs as essential as Social Security. Now imagine a benefit system where only a handful of experts know how its logic works. If one retires, the ability to update or even troubleshoot it may be lost. It isn't just about writing new features, it's the ability to fix errors, apply new regulations, or patch security flaws without destabilizing everything else. When knowledge declines, even a minor policy change can threaten to unravel a program serving millions. We saw what that scarcity looks like in practice during COVID-19. When unemployment claims exploded in 2020, states like New Jersey couldn't simply order more servers. Their COBOL-based systems required code changes that very few people could make. Governors issued public calls for COBOL programmers, and volunteer networks like the COBOL Cowboys or groups organized by U.S. Digital Response stepped up to help. Retirees were suddenly valuable again because they could do what modern training pipelines had not prepared new graduates to handle. It was one of the first times ordinary people saw that specialized knowledge in a 60-year-old language could directly shape who received vital checks. The imbalance is striking. Job postings asking for COBOL skills have actually increased in recent years, with hiring sites reporting measurable rises in demand. Yet the supply of qualified people continues shrinking. In other words, at the exact moment, when industries are fascinated by AI and robotics, the most irreplaceable roles in finance and public service depend on COBOL. For developers willing to learn it, that gap represents not just a problem, but a genuine opportunity. It isn't only private industry at risk. Federal agencies also face the same issue. A Government Accountability Office report found that several of the most critical U.S. government systems still run on outdated languages like COBOL, often tied to unsupported hardware and known security risks. Even more troubling, many agencies either lacked modernization plans or had incomplete ones. That means trillions of dollars in taxes, refunds, and benefits continue flowing through infrastructures vulnerable not only because of aging code, but also because of staffing uncertainties. The IRS is a vivid example. In 2024, it collected over $5 trillion in federal tax payments and processed hundreds of millions of returns. Much of that depended on software built around COBOL. With numbers that large, stability is non-negotiable, but stability still depends on enough skilled people to keep the system updated. Without them, both accuracy and security come under pressure. There are constructive responses beginning to take shape. The Open Mainframe project has launched resources to reinvigorate COBOL education, such as its COBOL programming course, designed to train new talent with modern tools. They also back frameworks like Zo, which let developers interact with old mainframes using interfaces closer to the tools they're already used to. Rather than treating COBOL like a relic, these efforts aim to fold legacy systems into today's developer ecosystem, making the skill more approachable and less isolated. The contrast today is sharp but revealing. We live in a world where people expect instant service through apps and cloud platforms, yet the foundational systems behind social benefits and bank transactions often rely on a handful of experts keeping decades-old COBOL alive. That's less a curiosity than a signal. For developers, learning these skills isn't about nostalgia. It's about stepping into roles where demand exceeds supply. For institutions, it's about deciding whether to rebuild, extend, or preserve the foundation that still handles the world's most critical flows of money and information. And that brings us to the larger takeaway. The deeper truth here is that the technology running so much of modern life isn't just hidden, it's older than most of the people relying on it. Its endurance forces us to rethink what progress really means, and whether advancing forward always comes from starting fresh or sometimes from sustaining what already exists. COBOL was introduced in 1959, yet it remains the engine driving much of the world's financial and government systems. From everyday bank transactions to benefits administration, industries still rely on it because replacing it is seen as too risky and too costly. That dependence explains why an estimated 220 billion lines of COBOL are still running worldwide, and why demand for maintainers surges whenever a crisis exposes those hidden systems. For programmers, legacy skills are less about nostalgia and more about practical value. Did this surprise you? Would you ever consider learning COBOL? Drop your thoughts in the comments and subscribe if you want more on real-world programming challenges and modernization. COBOL, the code that quietly still runs the world.